in ADS4, we actually have computational tools in the dual field theory, which will be the dual field theory, which is this ABGM, this three-dimensional superconformal Chern-Simons theory. We can compute the partition function of the dual field theory, and this exactly reproduces the black hole entropy of these supersymmetric black holes. And supersymmetry was a fundamental ingredient, meaning without supersymmetry, you cannot really achieve this matching, because you need supersymmetry in particular on the dual field theory to perform your computation, otherwise you're lost. So in this last lecture, I will just add 10 more minutes, let's say, to the last lecture, because I left you a bit on a cliffhanger. But in the last part, in the remaining 1 hour or so, I wanted to tell you something about near-extremal black holes, because as of now, the line of thought is that, okay, we have black holes with temperature, we have black holes that are stable with supersymmetry. What happens if you have black holes which are extremal, but they break supersymmetry? This is in general, in theories where you don't have supersymmetry, you can have this sort of black holes. And we can see, it was seen already from the 90s, that a paradox arises when you consider extremal black holes which are not protected by supersymmetry. So in particular, we will see that their entropy, their macroscopic entropy that you find at the gravity level, acquires quantum corrections. And this will mean that actually it will be drastically modified once you take into account the quantum corrections to black hole thermodynamics. To the extent that the density of states for these extremal non-BPS black hole, non-supersymmetric black holes, will actually go to 0 at 0 temperature. So it's a very drastic change of the picture that was achieved during the past, let's say, 5 or 6 years, due to a series of work that I'm gonna mention indeed in the last hour or so. Yes. In general, so what we consider here is that we consider quantum corrections to the path integral in the near-horizon geometry. So you could, it will have an effect, because from there you can compute the thermodynamic quantities and you can compute the entropy. So you compute the entropy of your solution. Let's say we don't directly see how the geometry changes, but we see how the thermodynamic quantities have some corrections. Yes.
Quick question. Is there any counterpart of any type of something extremal but not supersymmetric on
yes,
the CFT
indeed.
side?
No, oh, sorry, I meant in real world. No, okay.
No,
on the SUSY side, yes. So, well, I mean, you consider just, for instance, well, I mean, you consider in general, QFT. So the point is that in general, you will see that these black holes here, once you don't have supersymmetry, the quantum correction wash away their ground state degeneracy. So
right,
you
so
should
you don't
find.
Expect to see anything.
You
like
don't
that.
see, in a way, yes, you will not expect them to see in holography, let's say. So, I mean, at least according to the picture that we have up to now, we still need to, I mean, it's still a bit incomplete, but for what it means from holography is that you will not find any density of states at 0 temperature if you had to find a direct holographic system.
Thanks.
But it's okay, just taking 10 minutes a step back. So to recap what we did in last, because I left you with the solution. So if you remember, we have started with very simple solutions that were solutions without scalars, just with a hyperbolic horizon. We have computed their entropy. And then we have seen that it reaches one value, and these values was reproduced by the partition function of a BGM computed on a manifold, which is the Euclidean boundary of the black hole, like the Euclidean boundary where the black hole lives. And in this matching, I matched two quantities that arise in the dual field theory in the large n limit, so in particular limit, which correspond to the classical supergravity answer. In principle, the localization formula gives you like the full partition function with like this, you can expand in large n, but in general you get a big formula. You might or might not expand, but the thing that corresponds to the supergravity action is the large n limit. So also I left you with a formula before finishing. That was the formula that slightly generalized the BGM partition function to the case where you turn on 4 background vector multiplets, which are matter content like vectors, fermions, and scalars. And we've seen that, well, we have seen, I give you the formula, but basically the partition function of a BJM, always on S1 times S2 for the moment. Like, just I'm gonna write it here, so S1 times S2 achieves this form here, where all these deltas are combinations of the background fields in your theory. So this is the time component of the background vector multiplet gauge field, and this sigma f is just like the expectation value of the scalar in this background supermultiplet. Also, in order for the localization computation to have a result, you need to impose this particular constraint on your deltas, which we call the fugacities. So this particular setup here, meaning having a BJM coupled to background vector multiplets with 1 unit of magnetic flux, is exactly the quantity which is dual to the entropy of this kind of black holes, which I put like on the opposite side. So these black holes here arise as solutions to the BPS equation, to the SUSY equations, and to the Einstein's equation of this action here, which is the action of 4-dimensional supergravity. And indeed, so in this case, you have supergravity coupled to some vector multiplets. In particular, in this one, it's coupled to 3 vector multiplets, but I set them all equal between themselves. So it's like I had just 1 vector multiplets. And this is the prepotential that really, from which you can read off all the couplings between your fields here. Here I put it very schematically. But so we have a setup which is exactly dual to the dual field theory on the rigid background that I put there. So these black holes here are real black holes with a spherical horizon. They satisfy the supersymmetry equations. They have this metric here, this particular form for the gauge field. The gauge field is purely magnetic, which is this one. And also they are supported by scalars, which in this case, the scalar is purely real. In general, it's complex. And it assumes this form here. So notice that the fact that the scalar is non-constant is given by the fact that this parameter B1 is non-zero. I hope you all can read here. But in general, so if you have B1, which is non-zero and sufficiently high, the value of C, this parameter here, which appears in your work factor, can be negative. And if this is negative, it means that you can have two coincident roots at a radius which is minus C over 2G. This is like the 2 coincident roots. It means, in general, that when you choose the parameters appropriately, you can have a horizon. You can have a non-zero area of the event horizon, even if you have like a horizon which is a 2-sphere. For this, you need scalars. You need a theory of matter-coupled supergravity. Okay, this goes back to the last class. So for this solution here, I mean, you don't need to know more details than that, but just to let you know that this solution here satisfies, or at least exhibit, a lot of interesting physics, especially because the presence of scalars is such that this solution displays 2 different attractor mechanisms. So for instance, at infinity, so at the boundary, so at r goes to infinity, the scalars are such that the potential is extremized. So the scalar attain a constant value that extremizes the potential at infinity in order for your solution to have an anti-de Sitter asymptotics. And at the horizon, which of course there we have like 2 coincident horizon, r plus equals r minus equals r0, let's say. There is another function which is extremized, which for the solutions which are now under consideration becomes very, very simple. Let me just take the correct quantity. This quantity R is extremized, and its form is exactly equal to this one, sum over lambda, F lambda, P lambda. So it's a linear combination of the magnetic charges, like P lambda, which appear in the gauge field here, and this F lambda. F lambda are just functions, so I have to derive, so F lambda. There are some quantities which are function of the scalar fields, and they're nothing else other than the symplectic prepotential divided, differentiated with respect to X lambda. X lambda are the the, let's say, projective coordinates with which you parameterize your scalars. But okay, all these technicalities to say what? So this particular, so while at R goes to infinity, the potential is extremized, at the horizon, the quantity R is extremized. And this is the so-called attractor mechanism. That states that indeed, in general, when you have an extremal black hole in theory of supergravity, there is a quantity which is extremized at the horizon, and the value of this quantity at the extrema is indeed the entropy of the black hole. In general, these solutions that go from ADS4 to ADS2 times, I'm going to put here is S2, but also valid in the case where is where this manifold here is a higher genus Riemann surface. In general, these solutions go from ADS4 to ADS2 times S2. So the scalars on this thing extremize this, but also ADS4, they extremize the potential, so they are some sort of called as double attractor. So the scalars can do whatever you want, but their value is fixed by these two conditions at asymptotic and also at the event horizon. All of this is to say that we have a quantity here that is particularly, let's say, simple to write down, in terms of which we can write the black hole entropy. So indeed, if you write the black hole entropy, so this took a bit of time to people to just remassage the supergravity equations to get actually the black hole entropy written in some human form. And this human form, as you can really expect, there's a very suggestive form. So this is okay, let's put here proportion, but it has a coefficient in front of it that, of course, people took into account very appropriately. And the expression for the entropy is really this one. Sorry, I'm putting here, when I say these sections have always upper coefficient, but sometimes I get a bit confused. So, okay, sorry, x0, 1, 2, 3. Okay, and this lambda goes from 0 to 3. So the black hole entropy is obtained by this formula here, computed at the horizon. So x lambda at horizon. So at this point, you see that you have to just extremize this function here, and you get this formula here. So the same way, people said, okay, this is what happens at supergravity. So you have to extremize a particular function, and then this is what you get. This bears a very striking resemblance to another formula that I wrote down, which is really this one, right? So it really, if you map the sections like xi, let's put it x lambda at the horizon, into delta over 2 pi, you get exactly some, okay, let's put it delta, let's say critical. You get exactly some values that indeed also extremize this function here, right? So because indeed, if these values here at the horizon extremize these and give you this, then these values here, they're also critical for the same functional form, which is this one. So in this way, just to finish the topic that I left you last time, so you have that indeed, the fact that this solution is an attractor, so the attractor mechanism in supergravity, the fact that the scalars extremize a particular function here, inspired the so-called extremization principle, the I extremization in the dual field theory, in such a way that actually you have that once you take into account the extremization principle, S black hole is exactly equal to the logarithm of Z BJM at the critical point. So you have to extremize this function here. You find the delta critical, which are these ones. Once you plug this in here, you get exactly the match. So in this case, I wanted to show you this exactly because here we have matched one number very beautifully in a way. But here is just to match an entire formula, like with a specific dependence on your chemical potential, the fugacities, that before, in principle, there was no reason to really associate these things to the scalars in supergravity. But just by inspecting the two formulas and by drawing parallel between extremization principles, you get that really this formula here holds beautifully and matches. So a few other considerations just before moving to the new topic is that, so the black hole arises, so in order to get the black hole entropy, we had to extremize this function R here, right? So we have some critical values of these sections here. And thereby, we single out particular values of these deltas there. So this is for the black hole solution. So one is actually kind of like drawn to the question, okay, what if we do not extremize this formula here? Do we actually have gravity configurations that correspond to this partition function? And actually, the answer is yes. So the black hole solution corresponds to critical point of log Z BGM. So in general, black hole solution correspond to critical points, but it's not always a maximum. It can also be a minimum or so on. You just need to be a critical point. So the points which are instead not critical, so for the generic values of deltas, instead there are other solutions, and which are called black saddles. And I can give you the reference. They were found by Anthony Charles and Nikolai Bobev. And also for these configurations here, you don't actually have a black hole solution. So you have a soliton in ADS space that actually caps off smoothly. So they are Euclidean solutions, which cannot be weak rotated into a horizon. But for these solutions here, you can also compute the quantity that we really like in holography, so the on-shell action. So the renormalized on-shell action of these particular solutions that are obtained for generic value of delta S really matches the points which are here when I insert, in general, non-critical values for fugacities into this formula. So in general, the matching is more generic. So it is valid also for black hole, for configurations which are not strictly speaking black holes, but they're only black holes which exhibit this particular extremization principle, which goes under the name the attractor mechanism. Okay, so I think on this part, I have pretty much, okay, maybe I can just say one more thing, is that in general, so you also have that this delta critical here, this parameter here, they also, well, okay, in the dual field theory language, for those of you that know, they are the coefficients that appear in the, so these deltas in general here appear in the trial R charge of your dual field theory, and the extremization principle single out, by means of this delta critical, the exact R symmetry of your theory in the IR. So you have this nice parallel about like that is drawn between extremization principles in gravity and in the dual field theory. And also as a last thing, let me mention that, again, all this kind of matching were found first really in the context of these black holes. So in around 10 years ago, like in 2015 or 16. And then we have also like developed over the years another, many more computations of localization in the dual field theory that allow also to match not only these solutions that were the topologically twisted solution, this one branch of solutions, but we can also match the black holes which have also electric charge, which pertain to the other branch that I discussed in the previous lecture. And also including subleading corrections. So we didn't compute only the larger limit, but we find also subleading corrections, which are given, like in gravity, correspond to higher derivative corrections. Those are also, were matched in many different papers. In particular, Nikolai Bobev is one that is an author that really does a lot of this work. So, okay, if there are no other, yes? It's always so, these sort of solutions that are, you know, in which you have a magnetic field that satisfy the Dirac quantization condition, it's very similar to the one that you had. You always have a 1/4 BPS solution. So, whole No, no, in general, no. This is, in this, I have assumed that my solution is purely magnetic, like the one that I have written here. It's specific to the form of the killing spinor we have. And the form of the killing spinor of those solutions there is exactly the same as the one that I explained that we derived together. So like I use the same the same prototype of solution. This has more scalars and more fields and so on, but it's the structure is always there. And this implies this particular form for the attractor mechanism. If you change your supersymmetry properties, you still have an attractor mechanism, but it will look slightly different. It will have a different functional form. Yes. Yeah, exactly. They still have the same, let's say, they still have the same form in the sense that they also have a magnetic gauge field. They also have the same supersymmetry property, again, the killing spinor, but instead of having an infinite throat, let's say, being ADS2 times something, they cap off smoothly, so they don't exhibit an extremal horizon. So they are solutions which are purely Euclidean solutions. They cannot be weak rotated into a Lorentzian black hole. Contribute, yeah, they still contribute to the partition function and so on, but you find them only when the deltas are not tuned to the critical ones. You find them when the deltas are different, they do not extremize this thing. So the black hole is the only one that actually extremizes, they correspond to a critical point, not quite a maximum, but in general a critical point.
Those black saddles do not have any notion of horizon?
No. It's like they are purely Euclidean solutions that indeed they cap off smoothly as R2. So these are the near horizon geometry, yeah. Okay, they cap off smoothly as Euclidean space.
And they do have entropy?
In general, no, what you find for them is like you have to compute the on-shell action. So the on-shell action corresponds to that thing. For black holes, as we saw, the on-shell action is equal to minus the free energy, and then it matches log z. So we always need to go into reverse. We have to, the object that you match is always partition function and partition function and renormalized on-shell action. Then we know that the on-shell action has a meaning in terms of entropy. It's like it's directly related. You have to do some specific limit, but.
Yeah, so my confusion is, like, say, even though you have the partition function, doesn't mean that you can obtain entropy.
Yes,
okay.
Because in general, for these solutions here, you cannot have they don't satisfy like usual thermodynamics as a black hole, let's say. Okay, other questions? Okay, then if not, so I'm gonna move on into the last, very, very last part of my class. And to do so, I'm gonna raise the temperature a tiny bit. So I'm gonna take the black holes which are extremal. So we can start with a very easy example, maybe of Reissner-Nostrom black hole, like with charge. And we can start from the extremal solution and raise the temperature a bit. Let's see how the black hole reacts. Okay, I'm gonna write down probably for the nth time an extremal Reissner-Nostrom solution. So bear with me. Okay, so again, 2m over r plus q squared over r squared dt squared minus. Okay, the same factor. So okay, for this one, again, if you write down temperature and entropy in terms of R plus and R minus, right? So the solution admit inner and outer horizon. And again, so the temperature is given by the difference between these two horizons. squared. The mass, I mean, you can compute it, but it's also expressible as these two quantities. It's the sum of the two. And the entropy, again, is pi multiplied by r plus squared. So again, r plus squared is the outer radius, outer event horizon, is the radius of the outer event horizon. So for this one, we imagine, we imagine taking the extremal solution. So R0 is the extremal radius, which is obtained indeed when the mass is equal to the absolute value of the charge. So it's equal to the charge. But we imagine like making the following displacement. So we displace a bit R plus by this infinitesimal amount. I'm going to tell you all what this means like momentarily. Dot, dot. And we keep Q fixed. So it turns out that the temperature, so if we displace a bit the horizon according to this, and according to this, where lambda is an infinitesimal parameter, we get that the entropy, the temperature is given by this value here. And the mass and the entropy have a specific, let's say, behavior in this expansion, which turn out to be pretty much universal to every black hole which has an extremal limit. So if a black hole has a near-horizon geometry, which is ADS2 in the extremal limit, when you heat it up a bit, when you give a bit of the temperature by displacing these two horizons, this actually means that you put it a bit of mass. So you insert a bit of mass, so then the temperature changes a bit in this way. So the relation between the mass and the temperature is always quadratic. And the relation of the change in entropy is always linear. So this is S0 plus 2T over M gap. So this M gap is a very important quantity because now we're going to make a very useful plot. But it has this sort of expression. So it's the inverse of the extremal radius. So in particular, we focus on this expression here, which is something that indeed, let's say these relations here, were like the origin of a paradox in the low temperature black hole physics analysis, because of the following reason. So we see that close to extremality, the mass scales quadratically with the temperature. So if we have to check the mass of the black hole, the mass which is available to a black hole versus the temperature, so energy available to the with respect to the temperature, we plot something which is a parabola, right? So this is this formula here. However, the amount of energy needed for a black hole to actually emit a Hawking quanta scales linearly with the temperature. So this is the energy available to a black hole. And this is the energy needed to emit one Hawking quantum, so to emit radiation. So what happens here is that, so we have a parabola and a line. They intersect at this point, particular point here. This point here is exactly E gap or M gap. So what happened at this particular point? So we are in trouble, right? In general, you want, so for your thermodynamic description of your black hole, you want a black hole to have sufficiently large mass in order to be able to radiate away Hawking quantum. And in particular, you want the process of evaporation to be quasi-adiabatic. So you want really your black hole to be some sort of a reservoir with a lot of mass, a lot of temperature, and it emits Hawking quanta. But like in this region here, you have that the energy available to a black hole, which is the parabola, is lower than the energy that would be needed to emit one single Hawking quanta, right? Because I mean, the parabola is is under this other this other line here. So this line here, you just get from the Planck distribution. So it means that you cannot trust black hole thermodynamics, at least at the classical level or semi-classical, once your temperature are smaller than a certain temperature, and in particular, once your energy excitations are lower than a specific value of the mass, which is called the mass gap, which is exactly this one, once you insert indeed appropriate units. So this was a paradox that was found by Preskill and collaborators in a beautiful paper in '91. Which means that indeed, so if you take a black hole which evaporates and so on, once you go closer to extremality, you cannot really trust the thermodynamics really as we know it, unless some other mechanism comes to rescue the day. Another way to rephrase this is the fact that indeed, so in general, you have the third law of thermodynamics. So for these black holes here close to extremality, we know that they have 0 temperature, but they have non-zero entropy. They have a huge entropy. And you might expect that indeed, once you include quantum mechanics fluctuations and so on, all this entropy actually, all this degeneracy gets lifted. So this is pretty much embodies the fact that a black hole which is extremal, in absence of other symmetry, we cannot really describe it at the classical level. There's something that is really missing. So what we're going to do is we're going to describe here, we're going to have a method to compute the quantum corrections to this picture. And what we're going to see actually is that by adding quantum correction, if you don't have supersymmetry, the energy available to the black hole becomes this. So this orange line. So this is the energy that you have plus correction. So in this way, the black hole will be able to radiate very, very close to t equals 0. So we're going to avoid the paradox. On the other hand, adding this quantum correction in the absence of supersymmetry is such that the density of black hole states will also go to 0. So by plotting density of black hole states in function of the energy, we will see that if you have no supersymmetry, you get to 0. While in the semi-classical picture, in order to have a finite entropy, the density would go to a non-zero value. So this is once you don't have supersymmetry. If instead you have supersymmetry, so this is the case for the black holes like this one or the other one that we studied in the last 2 lectures, you have that supersymmetry comes to your rescue, and you will have a delta function here at the origin, which signal the extremal entropy. You have a mass gap, which will be exactly this quantity here, in which there are no black hole states, and then a continuous density of states. So in this picture here, the black hole cannot radiate in these windows of, let's say, phase space, in which this line goes under the straight line here. So there are 2 different ways of resolving paradox. One is valid for SUSY. So we are happy because the computation that we did here was actually correct. So the computation that we did here is this one. So that gives the extremal entropy is the entropy that you get for 0 energy here. But if you don't have supersymmetry, then this is like this is something that you wouldn't expect it before. But this solves actually this paradox that you have here.
Excuse me.
So,
may I ask you to explain again what a paradox is? Because
yes. So
I'm not very uncomfortable with this plot, because when you get a very near-extremal black hole, what I would think is that you need some mechanism to stop Hawking radiation to avoid it becoming a naked singularity somehow. So isn't that sort of protecting you from losing a horizon?
what do you mean? Sorry, I didn't get it.
If we have an extremal black hole, and so suppose that the black hole is extremal and it emits, for example, a photon, then at that moment it lost mass. It has a lot of charge, a little bit less of mass, and now it no longer is a black hole. So it is a singularity, a naked singularity.
Yeah, exactly. So, but this is a different kind of. So here I'm taking the perspective of like like a black hole which is thermal, and the black hole tries to go down to extremality.
Okay,
So what you're mentioning is if a black hole is already extremal, actually if it's stable or not, something like that.
Yes.
So okay, so if you want maybe, so from this point of view, what we're gonna see is that, yeah, I mean, this entire paradox stems from the fact that you want to take your black hole very close to extremality, but you see that you have some obstruction just in taking thermodynamics at face value, because at some point, the energy available to the black hole is not enough to emit a Hawking quantum, okay? If you want, maybe your paradox can be seen as, yeah, maybe this is also some sort of embodiment of the fact that an extremal black hole, which is not protected by symmetry, is unstable. Because, yeah, if it will emit a particle, the mass, unless the particle is BPS, then you will have a naked singularity.
Okay.
I don't know if that answers your question, but the perspective of this thing is like just to take an non-extremal thermal black hole, try to either spin it to extremality or give it charge such that it reaches extremality.
Yeah, I still don't see why exactly this is a problem, that it can't reach extremality. It's
not that it cannot reach. So if you want, so are you comfortable with this picture or not? Do you get to see why this is a problem?
No, I can't see why it is a problem.
Okay, so let's see. So if you want, so you get the fact that the energy available to the system, so which is the energy available to the system is the mass minus the mass at extremality, right? So if you want, you can take this as, I don't know, maybe it's more comfortable to just take it delta E, okay? This one is a parabola, right? So this is this line here, okay, scales quadratically. The energy that you need to emit a Hawking quanta scales linearly with T. So if you're here, you're fine, because the energy available to the system is more than what you would need to emit Hawking quanta.
All right.
Okay, but as soon as you start being, for instance, here, let's say at this point here, the energy that the black hole has is not enough to emit not even a single particle.
Oh, I see. So I cannot trust the Hawking calculation anymore because I don't have sufficient energy to do what Hawking says I should do.
Yeah, exactly. Because in general, in order to trust classical thermodynamics, you impose the fact that your black hole is a thermodynamic quantity in semi-equilibrium, and you want evaporation to be a quasi-adiabatic process. And so once you go lower than this, you have to kind of change your paradigm. You cannot trust the classical picture anymore.
I see. Thank you very much.
Okay.
In this plot between delta energy and T, what will be the line for supersymmetric black hole?
Sorry?
In this plot of delta energy versus T, what will be the line for the case of energy for the supersymmetric black hole?
Oh, I think in general, so I think that probably, okay, it will be a bit modified. It will come here, but then at some point it will just not be able to emit. There will be no line between this and this. This is reflected on the fact that in this particular interval here, well, okay, I'm using M gap or E gap, but this thing is exactly equal to this one. So you will have no black hole states that we will be able to excite, let's say, in this interval here. So I'm gonna mostly focus on this picture here, because it's the most physically relevant for near-extremal black holes, which, for instance, exist in our universe. So, for instance, black holes which are spinning, so Kerr black holes exist in our universe, and some of the observations really found out that there are some black holes, given from binaries, that spin very, very fast. So near-extremal Kerr black holes in our universe suffer from this paradox here. So it's something that, you know, we should be really worried about because it's, there are black holes which really seem to, like, I mean, this sort of particular models something that exists in our universe. So it's something that, yes, it would be really good to figure out. So I'm going to focus on this picture here, and I'm going to tell you why now, with a particular framework, quantum correction are really modifying this picture and make the correction like all the way above this extremal line. And as a byproduct, we will find that indeed the density of states, function of the delta, let's call it delta E, goes to 0 at extremality. Questions? Or at least, is this picture clear? At least, is the paradox clear? Why is it a problem? Okay. Okay. Then we are gonna do this, and we are gonna. Let me just take the correct thing. So I mentioned that the first resolution of this paradox in these two different scenarios were found by Iliesio, Turiaci, various different linear combination of these authors. If I'm not mistaken, around the 2020 and around there. I can give you more specific references by using theories of JT gravity. So by using theories that describe excitations above extremality. So JT gravity is a two-dimensional dilaton gravity model that describes excitations above extremality. And it turns out that you can also use some sort of localization also for JT gravity. And you get the exact partition function, and from this you can get the density of states, and you get this picture here. We are not going to do that with this, like in this lecture here, but we are going to do an alternative procedure that relies on the path integral in the near-horizon geometry. Why is that? Well, we have seen, indeed, that extremal black holes have a near-horizon geometry, which is ADS2 times S2, right? So ADS2. So if you remember, ADS2 has a particular feature. It has an infinite throat, right? So like if you depict it like as an infinite throat here. So it means that in a way, for extremal black holes, the horizon geometry, like it's a universe by itself. So the fields basically lose information of what happens inside. In this way, we are assuming the fact that indeed we can compute the path integral in the near-horizon geometry and exploit this some sort of approximate decoupling of the near-horizon geometry to what happens like the exterior of the black hole. So we're going to compute the path integral in the near-horizon geometry in the following way. So we're going to compute the gravitational path integral, which is in general, like, you know, it's an ill-defined object, but we're going to nevertheless compute it anyway in the saddle point approximation. So in just concretely, we are going to do this. Also, like all of this started from the work of Iliesio, Samir Murti, and Turiaci in 22, but there are lots of other references. And so what we're going to inspect to compute the quantum correction is the path integral in the near-horizon geometry. So gravitational path integral, Z-grav, which is defined as the integral over various different geometries of e to the minus s of g, where we integrate over different geometries that satisfy the same boundary conditions. So g goes to g bar at boundary. And so we're going to, so basically what we're going to do is like we're going to consider the throat geometry, so this ADS2 times S2. We're going to consider flux, like we are going to compute this thing on the saddle, in the saddle point approximation. So we're going to compute the semi-classical, let's say the classical contribution and the one-loop determinant. So in other words, we fix boundary conditions here at the mouth of the throat. And we integrate over fluctuations in the throat geometry. We're also going to fix the ensemble. In general, we're going to work with an ensemble of either fixed angular momentum or fixed charge, electric charge in this case. And we're going to use the saddle point approximation. Namely, we are going to compute, we're going to consider an action that you have seen many, many times. So the action that we get is, again, the action that we are going to use is going to be the Einstein-Maxwell action, right? That's the same one that we use many times, and we add boundary terms. One of which will be the Gibbon-Sokin boundary term that we know it already, we used it many times. So the S2 AdS2 times S2 is a saddle point, let's say a saddle. And so we're going to consider fluctuations of the form where the metric is G bar, where G bar is AdS2 times S2 plus a fluctuation H. And this fluctuation H, we impose it to be, for instance, normalizable. So our path integral in this case will be, let's say, entail working with the saddle point approximation around this saddle. By the way, we are allowed to work with this saddle here because this geometry per se solves the equations of motion. So this is not quite it's a geometry that you get upon the decoupling limit. You get it indeed via the decoupling limit, but also solves the equations of motion. So it's a solution per se of Einstein, Maxwell, and in general lambda theories. But so in the saddle point approximation, we are dealing with an object of this form here. I'm gonna write it down. So we are going to have exponential of minus I that depends on G bar. So this is the semi-classical part, computed on the saddle, AdS2 times S2. And we're going to have a path integral over the various fluctuations, the H. And this is what you get by expanding the action at quadratic order. And the path integral computes then the inverse of the functional determinant, which is indeed the one-loop determinant that you might have seen, I guess that all of you have seen in quantum field theory, for instance. Functional determinant of this operator D. So now we see, so the whole business of this quantum correction will arise due to the fact that we have zero modes in the path integral. And the regulation of these zero modes will actually give the behavior that I showed you in the two graphs. So what are these zero modes? So zero modes is something that arise in many different scenarios. Also, they arise in various gauge theories of condensed matter. But so what is a zero mode? So in general, if some fluctuation has zero eigenvalue, of D, then there is a divergence. Why? Because in general, once you compute the one-loop determinant, it's like morally what you're doing a bunch of Gaussian integrals. So schematically, you are integrating from -infinity to infinity a bunch of integrals, like Gaussian integrals. And this, as we know, gives square root of pi over lambda. So if some of the fluctuation modes, which I call H, have 0 eigenvalue, 0 lambda, then you have divergence here. So you have to integrate over an infinite domain, or in general, we will have an infinite number of 0 modes. In this one, if lambda is 0, then you have a divergence. Your path integral is not well defined, so we need to regulate these modes. So these modes are just a very large number, and they basically have 0 action but infinite volume. That's what gives rise to divergence. So we need to find a way to actually not really get rid of them, but to have a way to really regulate them and to include their contribution. And that is what we are going to do. So for our black hole configuration, which is this one, then we are going to compute what is this D. So luckily, Ashok Sen already did it for us. And it's so this D is what you get by expanding your action at quadratic order. So it will be an operator which will be for its second order in derivatives. And they will have as an input the background geometry. So indeed, in this case, our D-dimensional operator, I'm going to write it down. It's very big. But so I'm going to write it here, so then we can leave it on the side. So for Einstein-Maxwell theory, lambda theory, this, I'm just going to contract it with already with H, reads this way. So it depends on 4 indices, alpha, beta, mu, nu. It depends on G bar, okay, H, mu, nu. So I don't think I'm going to write down all the terms, but I'm going to write a bunch of them, so then at least you have an idea of what we're talking about. So plus we have also some other terms that involve the Ricci tensor. Well, actually, the Riemann tensor, and various contractions of the Ricci. Plus, also you have terms involving the gauge field. At least various contraction of the field strength. So these are all the fields that appear in your Lagrangian, plus dot, 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 plus terms. That, this I can write explicitly, they're very small. So terms that involve the cosmological constant. G beta nu plus lambda over 4, G alpha beta, G mu nu. So, okay, all I'm saying here is that this quadratic operator, and this was found already by Sen, Ashok Sen, which is one of the pioneers of this computation already in 2011. But I mean, so you have to basically expand this one, this action here, you plug this thing here, and then you expand it at second order in H. I also have included in the action a gauge fixing term, but I'm not going to show you here the precise form, but you have to take into account of that. So one can check that if you have this particular operator here, like complete with all terms, a result that we can borrow from people back in the 90s is that this particular operator here admits 0 modes, and these 0 modes were found by Camporesi and Higuchi. So these 0 modes are, we are going to find that these people have already found this HAB, or this HAB like something that is annihilated by this determinant D. So these modes that I'm gonna write down. So borrowing a result by Camporesi and Higuchi, 92. We have that H mu nu of this form, I n tau. Okay, maybe let me just rewrite. So for a background metric, which is ADS2 times S2, let's say Euclidean ADS2 times S2. So for a metric, we have to define a background metric, and the background metric, we take it ADS2 times S2, but since we are in the gravitational path integral, it's well defined in the Euclidean signature. So the metric that we are gonna deal with will be this one. Let me write it down somewhere. Well, okay, this is d eta squared plus sine h squared eta d tau plus r0 squared, and then this is d omega 2 squared. This metric here is ADS2 times S2, ADS2 written in Rindler coordinates, where eta is the radial coordinate, goes from 0 to infinity, and tau is the Euclidean time coordinate that goes from 0 to 2 pi. So on a metric, which is this one, this operator here admits 0 modes that I'm gonna write down. D eta d tau minus sine h squared eta d tau squared. So here we have a family of metric perturbations that are labeled, so they depend indeed on all these coordinates, and they depend also on an integer number, n integer. But we have to cut the values plus or minus 1 and 0 for a reason that I will explain just momentarily. So all these modes here, if you plug it inside here, or I also forgot here, HAB, H mu nu, okay? So if I plug these modes here, inside here, I get 0. What does this mean? It means that, as I will written down here, you have some modes which indeed it will integrate to infinity. Because if you have to perform a Gaussian integral, you will have a mode with eigenvalue 0. So these modes cost 0 action, but they're an infinite number, and they're really like integrated over an infinite volume. So this means that these are like become a problem, because it becomes your, like it makes your path integral divergent and not well defined. So we need to find a solutions for that. In general, you will have also 0 modes that that involve, so all these 0 modes will be, so the 0 modes that I'm gonna talk about, they will be symmetries which are left unfixed by the gauge. In particular, you also have symmetry that rotates, like you have isometries of the S2. So there will be rotational 0 modes. So there will be other contribution for that. For the moment, I'm just gonna, I'm gonna focus on these ones, because the isometry on the S2, they are the ones that in general, they're ensemble dependent, in the sense that if I fix the angular velocity, so they correspond to fluctuations in the angular velocity of your black hole. If you are in an ensemble of fixed angular velocity, then these modes are not allowed. So I'm focusing now here on these modes here because they are the universal modes that, so they are there in every ensemble. Whether you fix angular momentum or charge or chemical potential or angular velocity, they will always be there. I will mention the rest of them like around the end. But okay, I mean, Camporesi and Higuchi found these modes. And actually, these modes have also meaning in terms of diffeomorphism of your background geometry. You can check that H mu, you can get all these H mu modes, like I indicated with H, as Lie derivative with a vector H of the ADS2 times S2 metric. Okay? Where the vector field is this one. Is once again, it's a bit long to write down, but it is something that can be checked. Yeah, I'm aware that I'm writing down lots of formulas, but the end result will be very, very simple. So bear with me a moment. So, okay, so it turns out all these modes here were generated by acting as a Lie derivative with this vector here on the near horizon metric ADS2 times S2. But this also like makes it clear, if you do a bit of work, that if you insert these values here, so I told you here that these modes are there for n, which is an integer, but I have to not consider the values 0 and plus or minus 1. Why is that? Because if I take n equals 1, 0, minus 1 into this vector here, well, if I take n equals 0, this vector here becomes 0. But if I take plus or minus 1, these vectors here are actually Killing vectors of your metric. So it's Lie derivative with respect to a Killing vector of a metric of the same, like which admits this Killing vector is 0. So that's why I have to, I mean, there are no 0 modes for n equals 0 and plus or minus 1. And this will have consequences for the corrections to the path integral. So from this, I'm not gonna do, like I think we can do a bit of passages, but you can see that they correspond asymptotically to diffeomorphisms. That takes tau into tau plus f of tau, and eta into eta plus f prime of tau. So for those of you who are familiar, for instance, with the JT gravity and ADS2 holography, these diffeomorphisms here basically respect the ADS2 boundary condition, but they have a non-zero Shortian action. So there is a relation, so it's all tied together with the JT gravity story that if you have time, maybe I can tell you a bit later or in the break. But in general, so these modes here, they are really something that they are large diffeomorphisms that have a physical meaning. So, okay, so we have seen this infinite family of 0 modes that are there. How do we choose to regulate these modes? So they exist in the throat geometry here, and we don't know what to do. So if we just compute it at the same time as the path integral, it will ruin our answer because we will get infinity, right? So what, like Iliesio, Turiaci, and Murthy did is that they had the idea to regulate these particular modes by going a bit away from the throat approximation. So instead of considering a black hole with an infinite throat, we're gonna take one step back, and we consider a black hole which is slightly above extremality. So we regulate our geometry by including the first subleading term in temperature to the ADS2 times S2 geometry. In particular, if you remember that we did a particular scaling limit, like already like one of the first classes, from the extremal rise nostrum, we need a particular scaling limit to get to this geometry here. Let me refresh your mind about that. From the extremal rise nostrum, you have to perform this coordinate transformation here. R goes into R0 plus 4 pi t. And then also you have a constant, which I put it like a coefficient, which, well, okay, I'm gonna leave off the coefficient, but then this kind of hyperbolic eta over 2, and t equal to 1 over 2 pi t minus I tau. So if I get the rise nostrum solution, the extremal rise nostrum, and I plug in this coordinate transformation here, what I get is like a metric which is ADS2 times S2. So what I get is G mu nu bar, which is ADS2 times S2, so this metric here, plus, if I expand it and I take the first subleading term, or like leading in this term, I make a series in T small, and I take the first order, I get a metric which I call delta G mu nu. So G bar mu nu is ADS2 times S2. And delta G mu nu is equal, okay, that depends a lot on this coefficient that I omitted here, but okay, it has this form. Eta d tau squared plus d eta squared. Oh, sorry. Actually, yeah, okay. No, actually, let me see. Well, actually, I think I'm just gonna, this one, you can just use it, like you can expand it in Mathematica, and like the exact form you can, it's actually very explicit. I'm not gonna write it down here because it's a bit long. But what I mean is that you take this coordinate transformation here, this lands you at 0th order into the near horizon geometry, and at first order in T on this geometry here, that you take it as a regulator. In other words, so we have these fields here, which are 0 modes. So if you compute them against this second order differential operator, dH equals 0. But this D operator here depends on your background metric. So you have this if you compute this on ADS2. Now we are going to modify this operator here and compute it on this full geometry here, which includes a piece in T. And we're going to see how this value here changes. Because we don't want 0 anymore, 0 for the zero modes. We want to see how the eigenvalue of the 0 modes depend on temperature. So the eigenvalue will acquire a small non-zero value, and this will make us like able to regulate our path integral. So in order to find this, we're going to find the eigenvalue correction in perturbation theory. And perturbation theory in this case is something like you can use formulas that you find, for instance, in the Lippmann-Schwinger formalism, like in your quantum mechanics classes. They're very easy. I'm going to write down now. So the picture is this. So instead of using the throat, where we have the 0 modes, this is ADS2, we take the first subleading term. So we are going to fix ourselves here, and this is G mu nu plus T delta G mu nu. So we're going to compute our path integral into this regulated geometry. So the eigenvalue correction, we can use perturbation theory. And so we're going to write this kind of formula. So this is basically, we want to see how the this are the zeroth order zero mode. So zeroth order zero modes are this one. We want to see how the zero mode change by the addition of temperature. And they still have to satisfy this equation here, right? Because you got it from just the perturbation theory, where this operator here is the operator that I wrote down there, computed on the full geometry, including the T correction. This will give rise to this quantity here, which is the quantity that we are after. So it's the variation of the eigenvalue of the zero mode. Hopefully, this will be non-zero. If this is 0, then we are back at step 1, because our zero modes have 0 eigenvalue. But we will see that in perturbation theory, this will give a non-zero value. So at first order, so we expand this equation here at first order, meaning we keep all the terms that have one delta. And we get these equations here. Delta D, Hn0 plus D bar Hn0. So with Hn0, I mean the zeroth, like the unperturbed zero modes, which are this one, equals lambda n0 delta Hn plus delta lambda n H0n. So I take this at first order. I use orthonormality between the eigenvalues, and then it really looks like you will see that in order to compute this quantity here, I don't need the correction to the eigenvalue here. Sorry, this is this one. I just need this eigenvalue here and the form of the first order correction to this operator here. So this is like a result that you get, for instance, once you compute the perturbed eigenvalues in quantum mechanics. So if you're just interested in the eigenvalue correction, the formula that you should use, that you can use by taking orthonormality of a normalization for that one, is this. So we just need to contract the zero modes that are here with the first order correction in the quadratic operator computed on this geometry here. So I'm going back and forth on this stage, but I hope it's clear. So this gives you the first correction to the eigenvalue that enters in your partition function in the following way, because we have that log z equals to 1/2 sum over n, where this I'm taking just into account the contribution of the zero mode. Of course, the partition function will have also the prefactor due to the semi-classical saddle and so on and so forth, but the contribution from the eigenvalue correction will be this one. So they will appear here. So this will be the correction to the partition function due to the fact that we have this corrected eigenvalue. So are there any questions now? You see that? Yes. Go on. I'm just going to.
Yes, the zero modes are complex. So in that integration, strictly it should be conjugate, or we're taking real part?
I was a bit sloppy. In the actual computation, we divide it into real and imaginary part of the modes. So we double it, but if you want to work with complex modes, then yes, you should have a complex conjugate. What we did from the beginning is that we have divided this thing into the real part and imaginary part, such that they're both real, and then we use this thing as in a real basis. But yes,
so
in principle,
at the same
these are complex.
At the same, so you work in the real part here, and this correction are the same than the imaginary part you said.
Yes, exactly.
Okay.
So real imaginary part will give you the same correction.
Okay.
We just, of course, we compute it, and this is justified a posteriori. But
Okay, this, okay.
So the zero modes, before this procedure, the zero modes are related to some unfixed gauge symmetry, right?
yes.
You're saying that heating up the black hole somehow fixes this unfixed gauge freedom.
It's not that it fixes the gauge freedom, but it makes it's a way to regulate these modes by keeping track of their, let's say, their physical meaning. It's like I'm not something that I gauge fix them or not. I just let's say check how their eigenvalue varies in a geometry which for which their eigenvalue is non-zero. Let's see. I don't know how, like.
Okay.
So it's like, in general, if you have a divergence, for instance, a volume divergence, you impose like a cutoff, and then you do some stuff in such a way that then once you take the cutoff to zero, or to infinity, your solution is well defined. That's what we are doing pretty much here. We're just gonna modify the geometry in a continuous way, because we are really adding just a tiny bit of temperature in these formulas here, and then we see what we actually get. This is justified by the fact that the solution with a bit of temperature, I mean, it's still a solution up to order t squared is still a solution to the Einstein's equation. And so you're still working with a physical solution. And this is probably, so I don't know if it's the only way how to regulate this divergence. It's probably, I guess, the most natural way, meaning that you don't have a lot of parameters to play with in these solutions. Temperature is one of them, and it gives you a regulated solution. So this way, I cannot say that it's the only way to regulate, but it's something that seems consistent to do. Any other questions?
Chiara, this has some parallel with the appearance of Gribov copies or something like that?
No, in this case, no, because they will, I mean, we will have no, for instance, ghost zero modes. So ghost in our treatment do not play any role in this regularization.
Okay.
I mean, Gribov copies are like, I think, pathologies that you get once you somehow you don't gauge, or like you fix the gauge.
It happens because you fix the gauge, but you have like the ghosts, and the determinant of the ghosts vanishes, so it's become non-invertible.
Okay.
Yeah.
In this, yes. So in this case, it doesn't. So this doesn't hold because you don't have ghost zero modes. This is something that you can check.
Okay, but when you fix the gauge, you put some ghosts somewhere, right? Before calculating the.
Yeah, exactly. So I didn't show it in the.
Yeah.
I didn't show it here. The actual Lagrangian, yes, will include also ghosts. Just that they will not, for the computation that we're gonna do it here, they will not play a role. Let's say.
Okay.
So they will play a role if you add, for instance, angular momentum. There are some subtleties for the Kerr black hole solution. There, for the Kerr black hole in asymptotically flat space, there actually is a ghost zero mode. But here, for this sort of configurations that are just static, spherically symmetric, they will not be ghost zero modes. They can be proven, and we have proved those in our paper. So this will not be something that will play a role. So the procedure, I hope the procedure is clear. So like this thing is a zero mode of this operator here. So what we want to do is instead put this geometry as a regulator. What we're interested in, they are really the change in the eigenvalues for the zero modes, that from zero will become something non-zero. Hopefully, that's what happens. In order to compute them, we just use perturbation theory. And so the quantity that we're interested in this, and will appear in the variation in the quantum correction to your the partition function on ADS2 times S2. That's the strategy that we wanted to follow. So it turns out we have to solve this integral here. So you plug it into Mathematica in general. So because this thing is like this operator here on the metric, on this, you have to use this piece of the metric here. It's readily computed in Mathematica, and Mathematica stores it, but it's kind of like it's kind of long, let's say, to like to manipulate. And so you let Mathematica run a bit, but the upshot of all this is that the result that you get from this integral here is surprisingly simple. And it's very simple also for a solution which is rotating. For instance, for the Kerr solution, this is a complete mess. This is even worse, and you have to let Mathematica run for several hours. But the final integral that it spits out is remarkably simple. It's just nt over 16 R0. This is n. Remind that n needs to be bigger, like absolute value of n needs to be bigger or equal than 2. So it means that you have to take integers, but you cannot take 0 and plus or minus 1. Because as I showed you before, these correspond to isometries of so the zero modes are not there because the vector correspond to Killing vectors, so isometries of the ground metric. So we are really happy because this is a very nice result. So it's just in particular linear in n. Needs to be linear in temperature, of course, because we were considering like the linear, like first order imperturbation theory. But that is really a nice result. So we can plug this thing into here and compute the correction to our path integral. So I still have, I have 5-10 minutes, right? I'm very close to the end. Okay, so I take it from here. By using this formula here, I get that the variation in log z equal to, let's say, the sum, and greater or equal than 2. So here I just added the factor 2 to take into account that indeed you have both n positive and negative. I just, let's say, remassage this formula in this way. Log delta lambda n. So I take the sum inside and I make it a product. So this is log of an infinite product n bigger or equal than 2 of R0 over nt. And this is an infinite product that I choose to regulate via zeta function regularization. So I use, now I use this formula. Square root of 2 pi, 1 over alpha to the 3 half. So I take this, I apply it to this here. Like what really shows at the end is that delta log z is equal to 3 half, well, let's say log t to the 3 half over R0 3 quarters equals to 3 half log t over R0 plus dot dot dot, where dot 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 I included, like I neglected some, sorry, 3 over 4. 3 over 4. I mean, I neglected some finite, like finite terms that indeed we are not interested in. What we're interested in is really this term here that will give you the leading behavior of the partition function of log z in the near-horizon geometry. So putting everything together, so we have the following formula. So the partition function in the near-horizon geometry for a black hole is this one. So t to the 3 half, and then the exponent of S0 plus, okay, in case where you have an asymptotically flat black hole, I'm just going to write it here, q to the 3rd, t. plus other terms that I'm not interested in this moment. But so this is like shows the dependence on temperature of the partition function, like of the quantum corrected partition function on ADS2 times S2. So it means, like you can see from here, this prefactor here, like you have to exponentiate it because you have the log, so the partition function acquires factor t to the 3/2, which is in front of everything. And this is due to the quantum corrections. In particular, it's due to the regularization of the zero modes. This one instead is the semi-classical part. Do you remember that at the, so in one of the formulas that I showed at the beginning of this class, I showed you that the entropy goes, like if you raise a bit the temperature, grows linearly in temperature. So this is the classical part, and this is the factor that comes from the quantum correction. So what this means, if you have to plot, so this is the value of the entropy. If you take the Laplace transform with respect to the temperature, you get the density of states in function of the energy. So from this formula here, we extract the density of states that, unsurprisingly, as I anticipated, like shows a drastic correction with respect to the classical part, because due to the fact that you have this t to the 3/2 on top of it, like in front of everything, you see that when temperature goes to 0, this entire thing goes also to 0. And so you take the Laplace transform, to extract rho of E. And if you plot it, you get, so this is the energy, and this is the density of states. You get that the density of states actually goes to 0 when the entropy goes to 0. So these are density of states for extremal near-extremal. Well, I put it here, Reiser-Nordstrom black hole. So let's say also like it's the quantum corrected density of states for a near-extremal black hole, while the semi-classical value will tell you that indeed the density of states instead would not vanish. So this is a semi-classical value. You see that things will start differing quite a lot for very small energy, which means for very small temperature, the quantum corrected piece, which is this one, has a very drastic effect on the black hole entropy that makes the density of states actually go to 0. So it means that the entropy that you get actually from the semi-classical analysis is not quite real, let's say. So it is washed away once you take into account quantum corrections. In our case, our quantum corrections were fluctuations due to the fact that you have 0 modes. But that is basically the upshot of the entire picture. In the case of supersymmetry, in addition to these 0 modes here, you also have fermions, right? So you will have fermionic 0 modes, and the contribution between fermionic and bosonic 0 modes will actually cancel. So you will not have this, but will actually originate a delta function and a mass gap. So there is some range of validity, so I'm just almost done. So the formula that we got here has a particular range of validity. So you cannot, so we were working, for instance, in the saddle point approximation on this ADS2 times S2 throat. So in general, you cannot go very, very low in temperature, because if you go low at the order of e to the minus, let me see, what's the e to the minus S0, you start encountering, like the contribution of the leading saddle start being comparable to the contribution of saddles such as wormholes or other non-perturbative solutions. So for our computation, you cannot go quite to 0, but you have to stop kind of closer to 0. On the other hand, this formula here is also not valid for temperature very, very large, like let's say here, because if the temperature is very large, your black hole becomes non-extremal, so you are far away from the approximation in which your ADS2 is the leading saddle point. So that's also, there are some, yeah, indeed, limits of validity for this formula, but for sure, what this shows is that at least into this sort of regime here, in which you can trust, let's say, okay, here I put random values, but in general, you really see that around these values here, you see some drastic departure from the classical picture. So this is just to show that if you don't have supersymmetry, quantum corrections seem to be very, very dominant at low energy, and they alter quite a lot the pictures as we know it from classical thermodynamics. So in general, I showed you from going from lecture number 1 to 2 and 3, that indeed, like, we have seen a lot of things about thermodynamics of black holes. We've seen that we can reproduce their entropy, but we can reproduce it only if you have supersymmetry. If you don't have supersymmetry, they're very nice. And I mean, they're just very interesting effects that make what you think you know about black hole entropy not quite correct. So it's something that we still need. And there are also lots of other effects. There are also other modes, rotational zero modes, and so on, that I can tell you a bit more about. But it's something that this entire picture, so this is just a start. We need to see how various, let's say, effect, like also higher derivative corrections, how in general they interact with each other. But at least this is the state of the art of what concerns zero modes and quantum corrections. So for the moment, I think I like to conclude here.
Questions for Chiara?
Oh, come on, don't be shy.
Sorry, first, I didn't hear well what you say, why there is a restriction near to zero. I will expect that the expansion actually will work better near to temperature to zero.
Depends what you, sorry. So in general, what you put is, yes, it will, the approximation will work well, let's say, close to t equals 0. But once you are at the order of e to the minus s0, so in general, this is where other contributions that before were much, much suppressed with respect to the original throat geometry, might also play a role in the path integral. So two saddles will become kind of comparable. So you are not able to trust your saddle point approximation, or like, yeah, you're basically, your leading saddle becomes of the order of potentially another saddle, like wormhole or some other unknown configurations. So in general, once your temperature is the order of e to the minus s0, so once you're very, very close to 0, it's, yeah, your saddle point approximation, the starting point is not quite valid anymore.
Okay. And also, this zero mode, the zero mode without correction, the extremal one, can be interpreted as large diffeos coming from the ADS2, or?
Yes, exactly. So, yeah, in general, if you if you take into account the vector that generates this one up via the Lie derivative, so you know these things are made out of like this H is given as the Lie derivative of a vector with a specific vector that I showed you of this G ADS2 times S2. So this vector here, if you compute it what it is asymptotically, there will be some large diffeomorphism that will preserve the, yeah, in general, the matrix of ADS2, and that will also, if you compute the action on a JT gravity perspective for these diffeos, you get the Schwarzian. So there is a bit of an interplay between the dynamics that you find in these near ADS2 studies and these zero modes. Zero modes are actually some sort of to what you call the Schwarzian field.
Okay, so we can interpret it like we are deforming the the diffuse, I mean, it's like a quantity that says how far away we are from a large diffuse. I mean, when we use the temperature as a regulator.
So yeah, this will be like diffeomorphism that do not die off at the boundary, that will have a non-zero action.
Okay.
Particularly, will have this the Schwarzian action.
Okay.
And if you go through the formalism of JT gravity and you compute the in general the gravitational path integral in JT gravity, you actually find the same quantum correction as you find here. So let's say that the physical origin of these zero modes and the field which is responsible for the dynamics in JT gravity is the same.
Okay. Thank you.
I have a question. When you mention the wormholes, do people believe that they exist because of JT gravity, or because we have some intuition for higher dimensions that they may?
No, I think that is the range of validity. Yeah, well, I mean, in general, people just give a bit of the range with some placeholder values because, they believe that given from the intuition of JT gravity, there might be wormholes. Yeah, we don't know about them from the higher D perspective. It's just to be to put some disclaimer that there are some range of validity to our formula.
I have two questions. One is when you expand around Xi with T as a parameter, delta Xi have a scale dimension like an ER regulator because T is dimensionful, right?
Yes.
Or
what do you mean, so I expanded in T, so I just have let's say the eigenvalue equation, like the one that I showed you before.
The metric expansion.
Yes.
The delta Xi is have a dimension or not?
You mean delta? Okay, I was a bit sloppy with the dimension. So you mean the
like
thing
a
that
scale of longitude dimensions? Because in front of delta, was a T with dimensions.
Okay. I was a bit sloppy here with dimensions, but I mean, that is, so what you get from the decoupling limit is like G mu nu, like G ADS2 times S2 plus T delta G mu nu.
Yes.
Okay? Yes.
This delta is dimensionless or not?
No, I meant delta G as the variation of the metric.
Okay. Okay. It's not the perturbation. The only parameter is T.
Yes.
Okay. Sorry.
So, maybe I should have, okay, so, yes, so this is the metric that you get once you just take the decoupling limit and you take the first order in T. I call it delta G, but I could call it also G first order in T. So delta is like part of the definition of G.
Okay. And the other one is you calculate the one loop determinant of the all degrees of freedom and the only
no, I didn't do it all the degrees of freedom. Like
okay.
I just did this thing, the part that is from the zero modes.
Only zero modes. Okay.
Yes, of course. So the thing that I swept under the rug are all these dots. So of course I already like all the finite part, because in taking out this R0, they are trashed into this thing. But in general, in the one loop determinant, you will have all sorts of other modes. There are also actually other zero modes, as some of you were saying, that I just neglected here because these are the universal one. But in general, you will have also, like running in the one loop determinant, you have also, like factors here that derive from other massless fields present in your theory that you need to take into account. This will give rise to a part that will be terms which will be log of some other things, for instance, the area of the event horizon, like area and so on, that will just be finite with respect to T. So here I just took into account the dependence on T that is given from the zero modes. There will be other modes that, however, they will not give this sort of dependence. They will give rise to finite, like finite terms. So all of these corrections, log corrections of this kind, were computed by Sen. So Sen was the same person that studied a lot of these things via different, he used different methods, hit kernel and so on, but yeah.
I have two small ones. First one is, we started with the black hole in ADS, right?
Yes, this one is actually, you can do this procedure like as long as you have a black hole which has an ADS2 times
Right,
S2
that was
nearized
going to be my question. You can do the same with black holes in flat space.
So whenever you have, yes, so this is general. The formula that you will get will also depend on R0, where R0 is the extremal, the value of the extremal event horizon. If you are in ADS, this will also depend on the cosmological constant. If you are in asymptotically flat space, this is just the charge. But as long as your horizon, your black hole solution has an extremal ADS2 times S2, you can do this thing, and you can use these modes. So there are other configurations, like black holes in de Sitter, which have de Sitter 2 times S2 near horizon geometry, or also Minkowski 2 times S2. And their situation, like you can kind of borrow this result, and however you find some pathology in the norm of these zero modes. In ADS2 times S2, these modes here are well defined. They have norm 1, so they are normalizable. You can take them, and it's like there's no problem. If you have DS2 times S2 or Minkowski 2, you have problems like the norm flip sign, so you have negative norm. So these modes here become of norm -1. Or if you try to find them in Minkowski 2 times S2, you don't find that they are normalizable. You find a divergent mode. This is something that we are still we're still working on, let's say.
Okay.
But this is like, these corrections seem to be, I mean, at least for what it is in this formalism, T to the 3½ correction is universal. Whenever you have an ADS2 near horizon geometry, your black hole seems to behave like this if you have no supersymmetry.
And the other one I can ask you later. Any burning questions before we close for courses for today? Okay, not. We thank Chiara again. And now we can all go have coffee and check out what our friends and colleagues are doing. Yes, sorry. There's going to be a prize for the best poster each week, so let us know your opinions.
No, debemos escoger nosotros.